In this section, we'll look at properties of electromagnetic waves. First, let's look at the electromagnetic spectrum. The EM spectrum comprises everything from gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. Now, waves that have a shorter wavelength and a higher frequency have more energy and are typically more dangerous. So, for example, X-rays, it's not good to be in X-rays for a long time. It's even not good to be in ultraviolet light for too long because ultimately it breaks down cells and causes cancer. On the other side of the visible light spectrum, we've got infrared, which is the same thing as heat, microwaves, and radio waves. These, especially radio waves, are typically pretty safe. You can see that the wavelength of a radio wave is between 1 meter and 1 kilometer. They're low frequency waves and they have lower energy. They're also too big to really mess up your cells. Right here in the middle, we've got kind of the sweet spot. We've got visible light. Visible light comprises a tiny part of the electromagnetic spectrum from 7 times 10 to the 14th hertz to 4 times 4 to the 13th hertz. And it comprises a wavelength band from 700 nanometers to 400 nanometers. So quite small. It's small enough to fit inside of our eye, inside of our pupils, and not quite energetic enough to cause us problems like ultraviolet light can. The speed of light is constant. It's 3 times 10 to the 8th meters per second. And this rule for the speed of light, velocity equals frequency times wavelength, still holds. So, for example, if I was working with purple light, and that purple light had a frequency of 7 times 10 to the 14th hertz, if I wanted to know the wavelength of that light, I could use the fact that the speed of light, which by the way is often called C for celeritas, which means speed in Latin. But anyway, the speed of light is 3 times 10 to the 8th meters per second, and I could use this formula, velocity equals frequency times wavelength. Where the frequency I would plug in as 7 times 10 to the 14th, and the wavelength is unknown, and I could divide to get the wavelength of light. Just a reminder that nano, like 400 nanometers, means 400 times 10 to the negative 9th meters. Again, the energy of an EM wave is proportional to its frequency. Higher frequency and lower wavelength yields higher energy. Electromagnetic waves are named as such because they are a self-propagating chain of electric and magnetic fields. So here's a picture of that. You have electric and magnetic fields that are perpendicular to each other. And we've learned about how a moving electric charge can create a magnetic field, and a magnetic field can move an electric charge. So once you get that going, we've got this self-propagating chain. Again, it's in 2 planes, 2 perpendicular planes, and it has an orientation. Because it has an orientation, it can be polarized. So here I've got a picture of unpolarized light. Unpolarized light would be in all directions, all 360 degrees. And a polarizer would allow only one direction of light to go through. If we have 2 perpendicular polarizers, like we have in this picture, then no light will get through. And I'll be sure to do a demonstration in class of that. In the meantime, let me show you a simulation. Oops, I went to the wrong thing. Here we go. Let me show you a simulation. Here is a simulation of light polarization. So I'm going to rotate this first polarizer, and you can see when I rotate it 90 degrees, all of the light past it is blocked. If I rotate it only partially, then some of the light will indeed get through. If I rotate the next 190 degrees, then all of the light is blocked. So light travels at a constant speed except when it hits a transparent medium, and then it slows down. The measure of how much it slows down is called the index of refraction. So this is a formula for index of refraction, and we're going to be working a lot with air. Air is pretty close to a vacuum. So the speed of light in air is pretty close to the speed of light in a vacuum, 3 times 10 to the 8th meters per second. But let's do another, let's look at something else. Let's look at water. What about water? So here it says that N for water is 1.33. And the speed of light is 3 times 10 to the 8th meters per second. And we would solve for the speed of light in water, in that medium. I'm going to use the means extremes property to swap the 1.33 and the water. So I'm going to take 3 times 10 to the 8th, divide by 1.33. And we are going to get 2.25 times 10 to the 8th meters per second. So that's the speed of light in water. I wrote down some other common ones. The speed of the N value for Pyrex, for vegetable oil, and glass. And you might notice here that for Pyrex and vegetable oil, the N value is the same. And if I go to my photos here,